Okay, so again, we're talking about this object resting on the inclined plane. So we've gone from that flat position where the weight force is acting straight down to now we're going to incline it. Well, the Earth didn't change and gravity didn't change, so the weight force is still going to be acting straight down. The only problem is the surface it's sitting on is now changed. So the weight force is still acting straight downward. But like we said, that weight force is also now trying to slide the object down or make the object move down the inclined plane, which before the weight force was just pushing it against the surface. So now that weight force is going to get broken up into components that do two different jobs. So just like we had in the chapters before, we're going to look at how this weight force gets broken up into components. And it gets broken up into two components. There's a parallel component that's trying to pull it down the inclined plane. Some force or some reference books or online sources may call this the down the plane force, or the force trying to move the object down. I like to call it the parallel force because it's parallel to the inclined plane. The other part is a force which is perpendicular to the inclined plane. That's still the force that's pressing the box or the block of wood or whatever it is, that's pressing it onto the surface. It's now still acting at an angle, so only part of the weight force is creating that pressure or push into the surface. The other part of the weight force is trying to make it slide or move down the inclined plane. So this we call the parallel force or parallel component. And that parallel component, just like we did when we found the x and y components, we're going to use trig functions to do so. But this time the angle isn't from the x-axis. It's the angle of incline, or the angle that the inclined plane is tilted from 0 degrees, how much it's lifted upward. So this parallel component, the component trying to pull it down the plane, is found by taking the weight force and multiplying it by the sine of the angle of incline. Okay, so the parallel force is the weight force times the sine of the angle of incline. The perpendicular force the perpendicular component is then found by taking the weight force and multiplying it by the cosine of the angle. Okay, so our weight force is now doing two jobs, trying to pull the block down the plane and trying to keep it pressed against the plane. So let's finish the other forces that are acting on our block. Well, first, since it's trying to move down the plane, there's something stopping it from trying to move down the plane, especially when it's sitting there, and that would be the friction force. So in this case, the friction force is acting up the plane. So usually we call down the negative direction and up the positive direction. So in this case, when we're out talking about an object on an incline, right, the parallel force is going to be negative and the friction force is going to be positive. And remember, those forces that positive and negative are just giving you the direction. So the negative force is trying to go down the plane, and the positive force, friction, is trying to stop it from sliding down the plane. The other force we have acting on the object is the normal force. And the normal force is perpendicular to the surface. Okay, it's not opposite the weight force. The normal force is perpendicular to or opposite of the weight force. Let's take a look at what somebody asked me a question. All right. So let's take a look at how this works with a problem. All right, so I've got a 15 kilogram box resting on an inclined plane that is inclined at 15 degrees. What is the coefficient of static friction between the box and the plane? All right, so let's draw my box at rest on an inclined plane. And I've got a 15 kilogram box. So let's start by making our free body diagram. Okay, our first force acting is the weight force. Of course, since the box is sitting on the inclined plane, we have a friction force holding it in place. And since it's resting against the inclined plane, there is also a normal force pushing up on the plane. Now the question is asking me for the coefficient of static friction, right? What's that coefficient of friction that's holding that in place? So I know that the definition of the coefficient of friction is the friction force divided by the normal force. So I have to figure out what the friction force and normal force are in order to do that. And we're going to do that by taking a look at the components of the weight force, the parallel component and the perpendicular component. Okay, so the parallel component, like we said, was FW sine of the angle of incline, and we're told that that angle is 15 degrees. All right, so first off, let's figure out the weight force. The weight force is always mg, so that's going to be 15 times a negative 9.81. Do that on the calculator real quick. 15 times negative 9.81, 147.15. So I have a weight force of negative 147.15 newtons. So now I can figure out the parallel component. by taking the negative 147.15 times the sine of 15 degrees. So 147.15 negative times the sine of 15 degrees. Oops, 147.15 sine 15. There we go. 38.09. And that is negative because it is going down the plane, right? It's trying to make the object move down the plane, so that is a negative number. The perpendicular force or component is FW cosine theta. So the weight force is still negative 147.15 times the cosine of 15 degrees, 147.15 times the cosine of 15 degrees. Oops, 147.15 cosine 15. There we go. 142.14. So my perpendicular force is negative 142.14 newtons. All right, so I'll put those into my, add those onto my free body diagram. Oops, negative 38.09 newtons and negative 142.14 newtons. So the parallel force or a parallel component is much smaller than the perpendicular force or perpendicular component because the angle is so small. The bigger the angle, the bigger the parallel force becomes and the smaller the perpendicular force becomes. Okay. At 0 degrees, we'd have no parallel force or parallel component. At 90 degrees, we'd be in free fall, would all be parallel component. Okay, so the less the angle, the less parallel and the more perpendicular component you're going to have. All right, so let's take a look at what this means. Since the box is at rest on the inclined plane, it's just sitting there, that means we have a net force of 0. Okay, since we're at rest, so if the box is at rest, right, then the net force is 0, right? The object's in equilibrium. The forces are balanced. The net force is 0. Those all mean the same thing when an object's at rest. So that means that the parallel component must have the same magnitude as the frictional component. Okay, the parallel component and the friction force are going to balance each other out. The parallel component's trying to pull it down the plane. The friction's trying to hold it from moving down the plane. So those two are going to be equal in magnitude, but opposite in direction. You can see that on the drawing. Similarly, the perpendicular component and the normal force are going to be equal in magnitude and opposite in direction. Because those two things are going to have to balance out. So that means my value for the friction force is a positive 38.09 newtons. That's an 8 there. And my value for the normal force is 142. Normal force equal in magnitude, opposite in direction of the perpendicular force, and the parallel component equal in magnitude, opposite in direction of the friction force. So now that we have the friction force and the normal force, we can find the coefficient of friction. The friction force is 38.09 newtons. And the normal force, 142.14 newtons. Doing that division there, 38.09 divided by 142.14 gives me a coefficient of static friction of 0.27. Okay, so the coefficient of friction, the minimum, could be higher than that, but the minimum right now that's holding it in place is 0.27 based on the friction force and the normal force.